So we have the density function. Could be anything. I've just got x plus 0 for 1 plus x plus 1. Okay. What's the mass of an increment of dimensions delta x by delta y by delta z, tending to the point x star, y star, z star. Okay. Now it also helps to sketch a little picture of the scene. So I'm going to do that. And I kind of recommend it to keep reminding yourself what it is. We've already paused to do it. If you're doing this for the video, pause the video. Tell me what this is. Tell yourself what this is. Okay. Will you pause? Done this? See whether you're thinking right or not. But you know, what's it look like? It's just like a rectangular box. There's no reason to draw it that small. We do consider it to be a small box. Then it's got dimensions delta x by delta y by delta z. Density, well, we have this box contains a point x star, y star, z star. Pick any point in here. We said this point here, let's say it digs down to here and over to here. Kind of at this x coordinate, this y coordinate, and z coordinates like this. So let's just say this is a point x star, y star, z star. Then based on the sample point, density is rho of x star, y star, z square, which is the star square. This, okay? Evaluate the density at the sample point and then assume very specifically doesn't very significantly with our volume, but mass within this increment is going to be not writing explicit tangents on x star, y star, z star. And now I'm going to write out what I'm using for the density. And there it is. Okay. So now what's the mass? mass within the solid bounded by these 6 planes. It's going to be a rectangular region because it's bounded by vertical planes. Oh, well, not by planes parallel to the coordinate axis. Go ahead and see if you can do that. Okay, now this one's fairly straightforward. You can sketch the region, not helpful to do that. But it's just going to be a region. Let's see, x goes out to 2, y goes out to 6. So the x equals 0 plane will cut, well, that's the YZ plane. The x equals 2 plane is parallel to the YZ plane, 2 units in front of it. So we've got dimension 2 here. We got dimension 6 here. And then this goes from z equals 0. Oh, wait a minute. No, y equals 4. Here, sorry. Z that goes from 0 to 6. So we're going to then go up this high here. And we're going to come out. So down here, over up here, up here, up here. It's kind of a wireframe box, not bothering with shading and dotted lines, but it's 6 units in this direction, okay? Now, we want to describe this region. Values go from 0 to 4. So we imagine moving along the y-axis, bunch of points from 0 to 4. Okay. So here are the x intervals according to y values from 0 to 4. And we see that x for each of those is from 0 to. So these strips here correspond to subdivisions, partitions of the interval from y equals 0 to 4. And each interval then corresponds to a strip in the xy plane. Okay. And as x goes from 0 to 2, well, we can think of strips like this. So it might be that our typical increment here comes to one of these rectangles. Then z goes from 0 to 6. Now, I'm not going to attempt to sketch the entire rectangular solid divided into little cubes because that would get to be a real mess. But I can take the part that corresponds to this rectangle and it'll go up to this high. Just going to go up to about here. Similar to this last one. And then we subdivide the z-axis. And that corresponds to now these z values that I've got here are going to correspond to slices, boundaries and slices of this column here. So that our typical increment is here. And I can do something much like this last time, but it's worth drawing at least a couple of times. So here's a typical increment. And I'm waving my hands a little bit over this, but I'm going to say now that the total mass it's a triple sum of that looks something like this. Except if you do this as Riemann sums, you're going to have i's, j's, and k's as subscripts. So you would have like an x star ijk, a z star ijk, so forth, okay? And you'd have a delta xi and a delta yi and a delta z sub I. I'm not going to write that out right now. We'll just kind of get the general idea. We'll fill it in a little bit more when we do some integrals in other coordinate systems. So it's kind of a triple sum. I haven't written a sum from I equals 1 to n and j equals 1 to m and so forth. Okay. But we understand that this is a Riemann sum. I think you know how to write it out, but we want to develop that. But here's the overall picture. This approaches on a triple integral plus z over 1 plus x plus z dy dx dz. Now, you might not have written it out with x, y, and z in the same order. Since this is a rectangular solid, it doesn't matter what order these things are in, but in a minute it's automatic. So y goes from 0 to 4. X goes from 0 to 2. And z goes from 0 to 6. And you can put parentheses in here, but the purpose of the parentheses when we introduce this is just to understand that this integral is with respect to y. Then whatever you get here is integrated with respect to x between the x limits, and whatever you get there is integrated between the z limits. Okay. As a matter of fact, I'm going to change this a little bit because I want it to be consistent with the order in which I wave my hands over this. So I'm going to see if I can wipe out these limits and change the order of integration to match what I did. So ultimately, we said, first thing, we're not going to say y goes from 0 to 4. So that's going to be the first, or the integral we label if we're labeling from left to right. And that means that we're going to integrate with respect to y from 0 to 4. And that's the last integral we're going to do. Okay. And then we divided x, so we're gonna let x go from 0 to 2 and integrate with respect to x. And then z finally goes from 0 to 6 and we integrate with respect to z. You'll see why I did that in a minute, because I'm gonna change this picture just a little bit. But now I want to okay. So it's above this region of the XY plane, but it's below this plane. Okay. Now you should of course recognize this. It's a plane, you got a normal vector, 2i plus 3j. Okay. Uh, and plus k, but minus k. There it is. Okay. So you can kind of analyze that plane. You can visualize it. You can even kind of sketch it. Okay, not particularly difficult to sketch, and I will. But let's not worry about the sketch. What's your integral going to be? It's a little more than that. And we're really talking about maybe a region that looks something like this in some rotation. Okay. Although it wouldn't have a square base, base is 2 by 4. Okay. And this turns out to be a 4 by 4, doesn't it? How would we describe this region by inequalities? We have the inequalities for x and y. What's the inequality for z? Okay, I'm having just a little uncertain about this. Where's this plane? Okay, I can draw a plane. And again, I always recommend picture. It allows you to keep track of what it is you're trying to figure out. Well, the picture is going to be just like what we had before. Okay. Except that when it's going to be easier to draw if I change my plane just a little bit. So I'm just going to change the equation of the plane. I'm going to do 25 minus 2x minus 3y. Just because a plane that's sloping this way is going to be easier to see in the sketch than a plane that's sloping this way, which is somewhat in the direction we're looking at. Okay. So, yeah, we would want to rotate the coordinate system to do the other plane. Don't want to deal with that right now, but let's say we have this, okay? So, well, what's going to be the point on this plane that corresponds to x equals 0 and y equals 0? Clearly, it's not all to scale, but this is the point 0, 0, 25. Isn't that point clearly on this plane? If x and y are 0, then z equals 25. So that's a point 0, 0, 25. Okay, now above this point, we're going to go up to z equals 25 minus 2x. Y is still 0. Well, x goes up to 2x is 4, 25 minus 2x is 21. So I'm going to say this is the point 2, 0, 21. It's not quite as high as this one. And in the XZ plane, well, right there is our trapezoid. Okay. Then if we go out to this point where z is, or sorry, where y is 4 and x is 0, if y is 4 and x is 0, then we're going to be subtracting 12 from 25, and we're going to get 13. This point would be, sorry, 0, 4, 13. And this point out here, well, x is 2, y is 4. So it's going to be 2, 4, 9. I want it to clearly be a little shorter than this. So this is 21 units long. This is 25 units long. This is 21 units long. This is 13 units long, and this is 9 units long. So now we have something that looks like this. Okay. I don't want to draw too many lines in because I want to go ahead and draw my typical rectangle. Now, again, I can subdivide the rectangle in the x-y plane. I could take my typical rectangle like these here. Now I can look at the, well, I'm going to take a sample point inside of this rectangle. Now, can you see a rectangle and a sample point there? That sample point is going to go up to the plane. Aiming the thing right. Doggone it. Anyhow, it goes up to here. Okay, we go from the sample point up to the plane here. I kind of messed that up. These skewed lines caused me to succumb to an optical illusion that wasn't above this point, but you see what I'm talking about. Okay, so how high do we go here? Your sample point. Then this rectangle is x star, y star, 0. Okay. The point on the plane above that sample point it's the point on the plane corresponding to the sample point is Well, the z coordinate is going to be and I've got some coefficients in there. Let's try them how to fit this expression in space I have, it right on coefficients. But it's 2x star minus 3y star. In other words, if I've got the point x star, y star, 0, how do I go here? Right? Well, plug in x star, y star into the equation of the plane, and I see how high z goes. So here is that point. So that we can take this rectangle and build it up to this point. That's really badly drawn, but it's just like one of these. It's going to have typical increment within here. So now it should be clear that z goes from 0 up to 25 minus 2x minus 3y, right? There's my description of the region. So when I do the integral, okay, I don't want to do my z integral last. Okay. Matter of fact, I want to do my z integral before I do my x or my y. The reason it'll be apparent when I write this out. So I'm going to want my z integral be the first one that gets integrated, because I'm going to have to substitute this expression for x and y and involving x and y into whatever antiderivatives I get when I do my y and x integral. So I'm going to do my same density function. And my last integral is going to, sorry, my first integral, the innermost integral is the first, most last, maybe this one's first. But the first integral I do will be this. Okay. And that's going to give me a pretty simple expression that I can plug this into. And of course, 0. Okay. And that expression is going to have x's and y's in it. As before, I'll just choose to integrate y 0 to 4, then x from 0 to 2, although it's not going to matter at this point because none of these limits have variables in them. Okay, so we've got a question. Which might indicate I did something stupid, but maybe not. Up. Okay. This is probably indicates to me that we better. Okay. So, and this is a good time to do that because then we'll see how all this works out. Now, you should be fairly familiar with it from doing the integrals to that. But we've only been on that 2 days. It's middle of a busy week. And those integrals really aren't officially due until a week after they're assigned. It's good to get started on them because getting started on the integrals in 2 dimensions helps you understand what's going on in 3 dimensions. And the things that you have to do, the way things work out. Okay. Okay. So we're going to go ahead and do this integral. The integral from 0 to 4. 25 minus 2x minus 3y of plus z over 1 plus x plus y. X. So we start with this innermost integral. To do this innermost integral, we're going to do an integration of a substitution or a substitution. Say du equals dz. We treat x as a constant when we do the integral with respect to z. Okay, so ordinarily the du would be dx plus dz. But since x is being regarded as a constant, it's just plain old dz. So the integral becomes the integral from 0 to right, this one z equals 25 minus 2x minus 3. And it's going to be u over 1 plus x plus y. Z. Well, that's the integral, and then of course the other integrations are saying, so we look at this, right? Well, our antiderivative is u squared over 2, right? So this is going to be the integral from 0. Z equals 25 minus 2x minus 3y of, now I'm tempted to take this expression outside the integral sign, but that's going to make things long. So I'm just going to say it's u squared over 2 divided by 1 plus x plus y. And I wrote this out prematurely. So the way I want to write it is it's this evaluated between z equals 0 and z equals 25 minus 2x minus 3y. And the integral from 0 to 2, the integral from 0 to 4. Now, u is my temporary variable here for substitution, but my limits are still in terms of z. I could have expressed all this in terms of u, okay? U being x plus y and so forth, but that would get a little complicated. So I'm going to just do it like this. And now I'm going to rewrite this integral. Instead of u, it's going to be x plus z squared over 2 because that's what u is equal to wherever I set it. Okay. Now my denominator 2 here is going to go down here. Okay, so I've got a, I want to try to put parentheses here. But I'm still evaluating this from z equals 0 up to z equals 25 minus 2x minus 3y. Okay, what that is, then the integral from 0 to 4, the integral from 0 to 2 of quantity x plus z squared. Well, the upper integral, z is going to be replaced by 25 minus 2x minus 3y. And all that's going to be squared. And it's going to be over this minus x squared all over this denominator, because this denominator does involve c. Okay, so when I substitute this in here and then subtract what I get when I substitute 0 in here, the denominator is not going to change. So I can just write it all over the same denominator. You okay with that? So this is getting to be a little bit of a mess. That's going to give me integral from 0 to 4 of the integral from 0 to 2 of, do a little calculation off to the side. Well, I combine my x's, and then I've got to square this mess. Okay. And I don't really want to go on with this because it's just going to get messy. Okay. To demonstrate this and actually do the integral, I want to do something a little simpler. Now, there's nothing you can't do. It's simply a polynomial. But it's going to get a little tricky. But what you're going to get is you're going to get a polynomial in x and y over another polynomial in x and y. To integrate with respect to x and then with respect to y. Z's gone. You get this limit involves x and y, so it complicates this thing a bit compared to what it would be for this integral. Okay. And that integral still get a couple of substitutions. Okay. But that illustrates how it could work out. All right. Now, I do want to mention, we'll go on with some of these, but look at some of the intervals. We're usually integrating between planes isn't too bad. Sometimes it's comes out nicer depending what your density is. If you're integrating over, well, let's say above this rectangle and below some hemisphere. Hemisphere, maybe if it's centered at the origin, would be like, 3x squared plus 3y squared plus 8. Z squared equals 3. Yeah. Be like 3x squared plus 3y squared plus 3z squared equals 12. Which would be like x squared plus y squared plus z squared equals 4, which is just sphere of radius. Okay. Now that wouldn't be a good, if that sphere wouldn't contain this rectangle. Okay. it would only come out to about here, come out to here, but only about here. So maybe it's x squared plus y squared plus z squared equals, I'm looking at that 249, what, here. So from here to here is square root of 2 squared plus 4 squared, square root of 25, square root of 2. About a little over 7. Okay. So let's say the stair was x squared plus y squared plus z squared equals 64. That would be a sphere of radius 8, and it would come out far enough to you wouldn't need a radius of 8 to contain this, but we do wrong with what 4 squared, 2 squared is 20. Square root of 20 is 2 square root of 5. It's not 7 units from there to there. Something's gone haywire in my head. Anyhow, the sphere is big enough to contain this rectangle on the xy plane. X squared plus y squared plus c squared equals 64 would be fine. It would come out to about here. Then you could integrate from here up to the surface of the sphere. Want to move to what you do in cylindrical coordinates and then hopefully in spherical coordinates. So imitating my original question, let's say my density is rho of r theta phi equal, say, I'm using rho for my density. That's kind of okay when I'm in cylindrical coordinates. When I get to spherical coordinates, it's going to get real confusing, right? I don't want to use d because we've got dx's and dy's and dz's. So I don't know what in the world to use. Density. Sigma is not a good one because it's usually, sigma would usually represent a density over an area, surface area, something like that. But I'm going to use it anyway because I can't think of a better. But I could use an alpha or a beta, but sigma is often used for a density, but it's usually an area density. It's be a volume density. Okay, you got a mass of an increment bounded by I'm just thinking of notation of what R equals something. Um, oh, you know what? Excellent. It, context of spherical coordinates. I don't want spherical coordinates. It's a cylindrical coordinates, and hopefully you're familiar enough with that because we have covered it at least briefly at the end of the first chapter. Okay. So we're bounded by these three regions. This is two planes, but what are these? Okay. Containing point R star, theta star, Z star. Now the two and the two plus the twos here, the pi over threes here, and the fours here really don't have any significance. If I was thinking it more clearly, I might have done it a little bit different. But you'll see how it works out. Okay. So R star would have to be in this case between 2 and 2 plus delta R. Theta star between pi over 3 and pi over 2 plus delta theta, etc. That's a Gauss picture. The axis. So what we've got is we've got a ring. This is the ring that be the ring between R equals 2 and R equals R plus delta R. Theta between pi over 3 and pi over 3 plus delta phi. So this is wedge theta equals pi over 3. These things look almost parallel, but get wider. Okay. And then Z between 4 and 4 plus delta Z. Well, the plane Z equals 4 is at height 4. 4 plus delta Z is a little bit higher than that. So that our increment is going to be up here. Distance 4, let's avoid optical illusion. While ago. Not drawn very well, but you understand, I take this little increment down here and raise it up here. Now that increment ought to look a little bit more like the I have here. So it's gonna be like. So this is supposed to be same size and shape as this. I just can't get the tip of the chalk to go where I want it to. Okay. And then it's gonna have a height. So here's my typical increment above this increment down here. And it's poorly drawn. Need better instrument there. I should have got it maybe bigger. Um, okay. What are the dimensions? Well, this thing here, maybe looks. It's pretty close to being a cube. But because of the delta theta, it's getting wider. You know, this dimension is a little bigger than this one. Okay. This dimension is your delta R. This dimension is going to be about star delta theta. This one's going to be delta Z. Now, why is this R star delta theta? For the same reason it was R star delta theta in polar coordinates. That's the dimensions of this little rectangle, okay? You bring it up here and make it into a three-dimensional solid by adding a delta Z. It still has the same area of the base. So volume depends on your R star. Depends on your sample. None of this had anything to do with the 2 here, the pi over 3 here, or the 4 here. I just put those in there to make it concrete. So let's say now that our region is the upper hemisphere. R from 0 to 4. Theta from 0 to 2 pi, we recognize that is a circle of radius 4 in the xy plane. And zero less or equal to z less or equal to what? Well, if it's a hemisphere in the in an RZ plane, we would have to come out to 4 here. Have to be 4 units here. So it's going to look like this. That's slicing it along any R axis you might want to make. Okay. It's going to look like this. So if we know R, I can draw this with a few. Let's say here's R star. For this R star, Z goes from here to here. So Z goes from Z equals 0 to Z equals 1. There are two ways to answer this question. Let me make sure. Yeah, I don't think so. Yeah. Okay. Two ways to answer this question. One's geometrically. This is a sphere of radius 4, center to 2 origin. So I've got this triangle here. What are the dimensions of this triangle? This side is just R star because R star is our coordinate along this axis, right? And this is 4. So what's this? I'm going to pause and let you tell me. Okay, got a real quick answer there. Said 16 minus R star squared. I just had to kind of jump in, square root of. But yeah, you saw it. Pythagorean theorem. This is a square root of. Then I write it down backwards. It's got that R star in the brain. Square root of 16 minus R star squared. Okay. Well, that's what Z goes. There to the square root of 16 minus R star. Oh, 16 minus R. Okay. So there's your description of the region. If I have a density function, I could throw it in there. Well, actually, I do. Got a density function. So delta V is this. I'm going to use sigma delta V. I've got a sample point within this rectangle. So the density is sigma equals R star cosine of theta star. So delta M equals sigma delta V equals R star cosine of theta star times R star delta theta delta R delta Z. Sum of all my delta M's is triple sum of R star cosine theta star R star delta theta, delta R, delta Z equals the interval. Okay. What are the limits in the interval? Put it down here. It's going to be the triple integral of R squared cosine theta. You've got an R star here and an R star here. And of course, you got the cosine theta. The limits on my integral, R and theta both have fixed limits. Only Z has a limit that depends on anything else. So I probably better let dz be my inner interval. So I'll even use some parentheses here. I'm gonna take the square off of that R, and I want to emphasize that you always got to get then an R d theta dz or R dz if you like it. The R d theta corresponds to the arc distance at distance R star with a delta theta wedge. Okay, the limits of the integral. Well, Z is going to go from 0 to the square root of 16 minus R squared. Theta is going to go from 0 to 2 pi. And Z, I'm sorry, not dz. Okay, I'm going to dr. And then R goes from 0 to 4. That turns out to be a pretty accessible interval. You're going to end up with an R squared cosine theta. But since you're integrating first with respect to Z, that's not going to be a big deal. You're just going to get a Z. So you're going to have a square root of 16 minus R squared. And you're going to have an R to go with that, which makes your U substitution U equals 16 minus R squared convenient, because your du will be R dr. Since you got an R here in a dr, it's going to work out. Okay. So this geometry works pretty well in cylindrical coordinates. Okay. Now you want to look again at spherical coordinates, because you're going to ask you, but you're going to ask yourself the same question. If there's an R theta and a phi, what would your increment look like? First thing, you got to be able to visualize this increment. You don't have to, you can do it by symbols, but you probably won't remember it as well, probably won't understand it as well. You want to be able to try to sketch out. It's a little challenging. But to show yourself what's really going on in the spherical coordinates. I drew some pictures. Your book has better ones. Go back and review spherical coordinates, what the increments look like, and so forth. But if you're trying to do a mass in spherical coordinates, it's going to be very similar. You know, you have a rho squared sine phi, b rho phi, and all that stuff. And you want to understand why. Okay. The essence of applying an integral and knowing what integral to use comes down to knowing what happens in the typical increment. That's why first thing I ask is, what do you get within this increment? And here's what do you get within this increment? In physics, we're into some electromagnetism, mostly right now, conduction model for electrical conduction. And the physics text has a question, it's got a rectangular region and you got this current density function, and you want to know how much current comes out here. And it breaks it down. It says, okay, let's think of a simple delta x increment of this space. What can you tell me happens in this delta x increment? As soon as you can tell me what happens in that delta x increment, the interval just pops out at you. Now you want to go through at least this much of the process. You should be able to go through the whole process, all the substeps and everything. Okay, and I'll eventually do one like that. But right now, understand the process, especially what you're going to need as an engineer. Just repeat, take a typical increment. And then you figure out, okay, the increments go from where to where, what are the limits, what's the description of your region. So if you know what happens in typical increment, know how to describe the region, you do your integrals are easier. Some integrals are easier in rectangular coordinates. Certainly, you wouldn't want to try to do this integral in polar or spherical coordinates. Okay, cylindrical or spherical. Although I have plenty of time when I was doing like course, I wouldn't know how kind of challenging when you first see it, but it can be done. It's just a mess. Okay. Rectangular coordinates are as natural as heck. In this case, you know, for this region, you could also do this in spherical coordinates. It would work out nicely. That's what would you have? Have just rho going from 0 to 4. Okay. And it wouldn't be difficult to deal with this part of it. Okay. So there's an example of one that would be easiest in either cylindrical or spherical coordinates. Be a little tougher in rectangular. You'd have to divide. You'd have to describe the boundary of that circle down here in x and y coordinates. Would be bad. X goes from -4 to 4. Y goes from negative square root, so 16 minus the square root of x squared to positive 16 minus the square root of x squared. Just same expressions. But the integration is going to be a little easier here. Okay, so you know the coordinate systems, you try to figure out what coordinate system is going to work best for the thing you're trying to integrate. And then you get to the last section of chapter 15, where you can create weird coordinate systems and do it, but we're probably going to omit that. To get the polar, rectangular, and cylindrical. It's about all people usually get out of this course. And if we get to the integral theorems, it's worth sacrificing that one thing.